Welcome back to our class on machine translation. Today we're going to look at IBM Model 1 and the EM algorithm. This is a very ancient machine translation model, actually over 30 years old, but it's still relevant today because it's used in word alignment and it's also, this class is a nice introduction into the EM algorithm. So let's just start simple. So we're gonna root our translation model in lexical translation. So the key step is that we're gonna translate a word at a time. So let's look at that first. So how do we possibly translate a word with a computer? Well, we could also just feed it a dictionary. So we can look up the word in an electronic dictionary. It's the kind of digital version of the dictionary you might have on your shelf. And it says, for instance, for the German word house, that its possible translations are house, building, home, household, and shell. So there are multiple translations. Some are probably more frequent than others. So in this case, the word house and building are the most common translations. And there's really just one really strange special case. The translation of house into shell is really just in the context of a snail. So in German, the shell of a snail is called its house, so the snail is carrying its house around with it. So also from now on in all the lectures, we translate from a foreign language into English, just to kind of keep things simple. When I talk about a foreign language, it's always the input language. When I talk about English, it's the output language. So if we had a parallel corpus and these numbers are completely made up, we might be able to collect statistics like this. So we can look at the translation of the word house in this corpus. And you find maybe the English word house 8,000 times, building 1,600 times, home 200 times, household 150 times, and shell 50 times. With these statistics, we can do the same thing that we have done so far in estimating probabilities, just do maximum likelihood estimation. So that should give us a probability distribution where the word house has a probability of 0.8, the probability of building has a probability of 0.16, and so on. So, and able to do that, we need to have an alignment of words in the corpus we have. So we assume we're going to get a large collection of sentences that are translated, and that's a fair assumption. This kind of data is plentiful. So you have a lot of sentences with their translations that you can do pretty robustly with automatic methods. But we're not going to get anybody align these words up. So this is the challenge we're going to tackle on head on today. But let's assume someone did that for us and aligned up the sentence and said, for instance, that the word das is a translation into how, into the house is a translation to house, is a translation to is, and klein is a translation to small. So let's formalize that. So we're going to number the word positions 1, 2, 3, 4 on the German side and 1, 2, 3, 4 on the English side. So that defines an alignment function. So we're going to have a function A that maps English word positions to a German source word. So it's a bit reverse of what you might think. So we're translating from German to English, but the way we do the mapping is we're going to map each English word to a German word. So we basically have to explain each English word where it comes from. So we basically say each English word points to a German word where it comes from. So English word position I points to a German word position J. In this case, it wouldn't really make any difference. The mappings are all just 1 to 1, 2 to 2, 3 to 3, 4 to 4. Okay, obviously, it's not always going to be that easy. German has this nice property of not having to start the sentence with a subject, so you can also start the sentence here with this adjective. Klein ist das Haus is a perfectly fine German sentence, Definitely a sentence that emphasizes the smallness of the house. But it's a perfectly fine sentence, but then the alignment looks like a bit more jumbled. So again, Klein is a translation of small, so you have the alignment link there, and so on. So here the alignment function looks a bit more complicated. So let's look at the word small here. So this is English word position 4. It's mapped to word position 1. What can also happen is you have a German word like klitzeklein that maps into two English words, very small. So that's no problem at all. So that just means that the word at the fourth position here maps to that fourth position word over there, and the word at the fifth word position also maps to that fourth position word there. So we can do that too. What we can also do is dropping words, so we don't actually have to account for all the German words. So the word das here is not aligned to anything, but the function is still fully defined because we just have to find values for all the English word positions. So inserting words is a bit trickier, so now we have to come up with something. So let's just say we introduce the word just in there. That doesn't add too much meaning to the sentence. Just kind of emphasizes a little bit the smallness. And let's say that was not done in the German sentence. So what we're going to do is we introduce a special German word called null that we're going to give the word position 0. And then the mapping of the word for, the fourth word just, to the word 0 here, null, is done that way. Okay, this looks all pretty good. You might have noticed one issue with that, which is, yeah, we can map a German word into multiple English words, but we can't map an English word into multiple German words. And we'll leave that aside and we'll come back to this at the very end of this class. So that's definitely a serious flaw with this model. And there is a solution to that we're just going to introduce at the very end. So for now, we'll just ensure that we just have to explain each English word with a German word. Okay, that's all you need to do IBM Model 1. So the formula looks more complicated than it needs to be. It's really just a very simple principle that's behind it, which is based on the alignment. So let's introduce some of the variables first. So now in bold F, we're gonna label sentences. So the bold F is the sentence, the foreign sentence, which consists of a number of foreign words, foreign word 1, foreign word 2, and so on, so on. LF is the length of the foreign sentence. And the English sentence E, which also goes from the English word 1 to English word LE, where LE is the length of the English sentence. So the alignment function, again, is we're going to map each English word to a foreign word according to an alignment function. So someone also gives us an alignment function. And then we can compute with that the probability of the English sentence given the foreign sentence and that alignment function. Okay, so how do we do this? So we have to explain each English word. We're going to loop through all of them, J1 to the length of the sentence. So we're going to loop through all the English words. We explain each English word. What do we explain each English word by? Well, by the foreign word that J is aligned to. So A of J here maps to an I, is a foreign word position, and that's the foreign word that the English word is explained with. So we basically have to explain each English word, and we're going to do this by mapping it to some chosen foreign word J according to the mapping function. So that's really the heart of it. This stuff here at the beginning is just there to make sure that the whole thing is a proper probability distribution. For all practical purposes, you can just really ignore that and not worry about it much. We'll never really do anything with it. It's just kind of there as a mathematical artifact that ensures that we're doing actually here probability distributions. So the essence of a probability distribution is that all possible English sentences could possibly generate it. Um, the probabilities of them add up to 1, and if you just plainly do this, that's not going to happen. Okay, let's go through an example. Let's say there's some magical process like the one we outlined before. Someone gives us these translation tables that say the word das maps to the with a certain probability, to that with a certain probability, to which with a certain probability, and to who with a certain probability, and to this with a certain probability. And the same thing for the other words too. So house, that it translates as house, is as we had previously, 0.8 or 80% probability. So these are the translation probabilities that we're going to call T here. So translation probability of E given F. Okay, so probability of E and the alignment given the foreign sentence is, well, these are the translations chosen by the alignment function. This is our normalization that I said, let's ignore that. So we're ultimately left with just kind of multiplying up all these probabilities that we pulled out of here. So there's 0.7, 0.8. We just always went with the most likely translation. Nothing too sophisticated happening here. Okay, that's a translation model. We have an input sentence. We choose English words for them, multiply up the word translation probabilities. There we are. It's clearly very simplistic. It doesn't take into account reordering, but what we should keep in back of our mind, we will combine this hopefully with a language model. So maybe the language model takes care of word order. But okay, let's just leave it at that. Okay, so that sounds all good and fine. The big open question we left out was where do we get these word translation tables from? Or phrased a different way, where do we get the alignments from? And that's exactly the problem we're going to tackle now. First of all, to get some intuition into this process, this is a nice kind of toy example that you can work yourself through and try to figure out by hand how do you discover this stuff. So this are made up languages. The underlying secret behind it, this is actually taking English and Spanish sentences and replacing them with made up languages, Centauri and Arcturian. But if you stare at this long enough, you probably get some idea about what should be happening. So you might see that you have your Sprock and Dat here, and you have Sprock and Dat here too. So maybe they're related. And you can actually work your way through this. And by doing this kind of co-occurrence, things that often frequently co-occur with other words, maybe that gives you some insight. Some words are also somewhat similarly spelled, so maybe that's in cue, and kind of figure this out. So I actually encourage you to go through this exercise here and maybe develop some intuition about how you can figure this out, and then maybe that's some guidance for how a machine can figure it out. Okay, we're now going to turn to how a machine is going to figure it out, and this is where we introduce the EM algorithm. So here's a problem we have to deal with. We want to learn these lexical translation models. So the key thing we have to learn there are these lexical translation probabilities. So you want to learn these lexical translation probabilities from a parallel corpus, which is a big collection of sentences with their translations. However, we can't just do maximum likelihood estimation because we do not have the alignments. So it's a bit of a chicken and egg problem. So if someone would do the work and line up all the words and mark that up, And people actually have done that, but really only for a few hundred sentences for testing purposes. It's a lot of work. Then we could estimate the parameters of a generative model. So this is just we have alignments. We just basically did what we alluded to at the very beginning. We just count up how often is the word so mapped to that word, how often is the word house mapped up to the word house, a building, and just collect counts. So then you have the counts, you do maximum likelihood estimation. So this is something we have now been doing last lecture, and we have been kind of alluded to this lecture. We know how to do this. On the other hand, if we had these parameters, so in this case, we know for each word what are the most likely translations, then we can estimate the alignment. So we can just say, let's go through the English sentence and just pick for each English word the most likely German word and draw that alignment link. So that way, if we have a model, we can actually create this kind of data. So the problem is we have neither. So we have a very good process to going from alignments to lexical translation probabilities, and we also have some good idea how to do if you have lexical translation probabilities to get to the alignments. But we don't have either, so we don't even know how to start this process. So this is exactly the setup for the EM algorithm that deals with incomplete data. So in general terms, if we had complete data, we could estimate the model. So in our case, if you not only had the parallel sentences and the words in them, but also the alignment links, you could easily estimate the model. And on the other hand, if we had the model, you could fill in the gaps in the data. So EM stands for expectation maximization, and it breaks out the algorithm actually in two steps, the expectation step and the maximization step. So how does the EM algorithm able to accomplish this? Well, the trick here is it's an iterative process, and we just basically we just come up with a model. If we come up with a model, so we just make up a model here, then we can do this. And then we have the gaps in the data filled, so we have complete data, and then we can do that. And we kind of just iterate around. So we initialize the model, for instance, by assigning uniform translation probabilities or just random values, and then assign probabilities to the missing data. Then that's the first step. So this is we fill in the gaps in the data with a model and then estimate model parameters from the completed data. So this is the other step. You have the completed data. Well, it's estimated, but we just pretend it's true, and we estimate a model from it. And then we iterate these two steps until convergence in practice. We're just gonna do this maybe for 4 or 5 iterations. Okay, how does that work out? To give you a very simplistic but instructive example, let's say all our data just looks like this. We switched for French just to mix it up. So you have a bunch of French sentences, la maison bleue, la fleur, and they are mapped to English sentences. These are, obviously very short fragments. The house, the blue house, the flower. So you have 3 sentence pairs, and you might have some additional data. So the initial model is all the probabilities are equally likely. So we're just going to come up with a uniform model that says any word in the English vocabulary is equally explainable by any word of the French vocabulary. So the might be generated with the same probability from maison as it is from the or from bleu or from fleur and so on. So we're not gonna make any kind of, we're not gonna put any kind of prior knowledge into this. So everything is equally likely. So we're still gonna learn from this data that the word the is aligned 3 times with the word la. And yes, it's also aligned to other words. For instance, it's aligned to the word house, maison, twice. It's also aligned to the word bleu once. And it's also aligned to the word fleur once. But 3 times it's aligned to la, twice to maison, and only once to house. So just based on these core current statistics, we would prefer that the is probably more likely to be translated, a translation of la, than any other word choice. So that's our first model. With that model, so this is how we estimate the first model from that data, where the data was all alignments are equally likely. Now we are going to apply this model to the data. So this is illustrated by these links here, where la and the are aligned a bit stronger than the other ones. So that means when we look at the sentence pair, we're gonna prefer that the is aligned to la than to other words. Then again, we assess all these possible alignment possibilities. The key thing is here we're gonna consider overall sentence alignment scores and estimate counts from there as well. So now we don't count everything equally, we're gonna count things higher if they're more probable. And if you can do this for a while, maybe by magic, the EM algorithm reveals then the underlying alignment here. And with the alignments, we can estimate the translation probabilities. Okay, so that's the basic intuition. So just kind of be clear about the program. So the EM algorithm consists of 2 steps. The expectation step, where we apply the model to the data. So parts of the models are hidden. Here are the alignments. Using the model that we have, we assign probabilities to possible values. That's the expectation step. The maximization step estimates the model from the data. So we now take these assigned values as fact and collect counts over that, weighted by probabilities, and estimated model from the counts. We iterate the steps until convergence. So we need to be able to compute 2 things. In the expectation steps, we need to compute the probability of sentence alignments alignments between words on a sentence level. And in the maximization step, we need to do count collection. The maximization step seems to be pretty straightforward. Okay, let's kind of go through this example here of a very, very tiny sentence pair, la maison to the house. And let's say we already, not at the very, very first iteration, but we've already a little bit further down. And these are the numbers we have, that the being explained by la is 0.7, the being explained by maison is 0.1. There are also other words that maison can translate to. The probability that la translates into house is 0.05, and the probability that maison maps into house is 0.8. So it's an okay model. It still obviously has some wrong probabilities in there. So we now look, and when I said earlier sentence alignment, I mean we're gonna look at word alignments for whole sentence pairs. So here is one possible word alignment for a whole sentence pair. So this is actually the correct one, where la and the are mapped up, and maison and house are mapped up. So what do we have here? We have mappings between words. We have an alignment, we have a source sentence, we have a target sentence. we actually have a formula for that. That's IBM Model 1. IBM Model 1 was exactly made for this case where we have an alignment function, we have a foreign sentence, and we can actually then compute this. So given with that, given the foreign sentence, how likely is this particular alignment and this particular English sentence? We just pull in the numbers. We did this before. These are now without the normalization. We're just gonna literally multiply up the two probabilities involved here. So how do we end up with 0.56? Well, we multiplied this and that. 7.8. 7 times 8 is 56. Okay, so we're going to do this for all the other possible alignments. So there are 4 possible alignments, and why is that? Because we have to explain each English word, and there are 2 choices for the, and there are 2 choices for house, so there are 2 times 2, 4 choices in total. So here the is still aligned to la, but now house is also aligned to la. Here now the is aligned to maison, house is aligned to maison, and then here's this aligned to maison, and house is aligned to maison. So let's look at the second one. So the aligned to la, house aligned also to la. So the aligned to la, that's still up here. House aligned to la, that's this number here, not very high. So we're multiplying that up. 5 times 7 is 35, and here 35 shows up. So 0.035. So that's the probability for that. And we can do this with all the other numbers. So this here is 0.8 times 0.1, and this here is the really unlikely 0.1 times 0.05. Okay, so these are the 4 possible values. So this is just the straightforward application of IBM Model 1. It gives us the probability of the English sentence and the alignment given the foreign sentence. However, the English sentence is given. We are really interested in the probability of the different alignments. So we're interested in the probability of the alignment given the sentence pair. So it's slightly different. And we're going to go through the math about how to do this and mathematically. Right now, intuitively, the task is we have all these numbers here. They don't add up to 1. They have to add up to 1. So we're going to normalize it that they add up to 1. So we scale up each value a little bit so they end up adding up to 1. Okay, and that's it. That's the probability. We filled in the gaps in the data. And now with the gaps in the data being filled, we can now collect counts. So what's the probability? What evidence do we have for la being the explanation for the word the? Well, it occurs here. So we're gonna take this number, and it also occurs here. So we're gonna take this number. So these are the counts. So the probabilistic counts in this time for the and la being linked up. So it's not happening here, and it's not happening here. And we're going to do this now for all the other word translation possibilities that exist in the sentence pair as well. So let's get a little bit more formal about this. So IBM Model 1 and EM, so the expectation step. So this is the task of coming up with a probability for an alignment given a sentence pair. So let's do one thing, which is applying the chain rule, because it gives us here P of A, EA given F. That's what we already have. That's IBM Model 1. That's the definition of IBM Model 1. We have that formula. So that we already have. So this one we still need to figure out how to compute. So how do we compute this? Well, intuitively, we have to sum over all possible alignments. So this is now a bit mathematically sloppily. We have alignment function. We're just gonna go over all the possible values for this alignment function. So what that means in practice that each word might be aligned to anything else. So we're gonna basically figure out what is word one aligned to, and it can be to the null token all the way to the length of the foreign sentence, and then we're gonna go through this with everything else. So this should scare you a little bit because we have a number of sums, so this is exponential in the length of the English sentence. Okay, otherwise what we have here is IBM Model 1 and it's just filled in here. So this is now the formula as it should be done. So um, this is a bit scary because we have sums and then we have sums and then we have sums. So if you think about it in a computer program, you have a for loop, another for loop, another for loop, another for loop. That is exponential. That's not good. Um, so what can you do about it? So we're just gonna do a little bit uh, have like give some hints about it. While this part here, we can move it out, and we're just generally not very interested in it. That's the normalization. Okay, that hasn't really solved our core problem of this sum, but apparently you can just replace the sum with this here. So this is a trick they can do um, that makes it much more tractable. So then you only have a product and a sum. So if you're not interested, you can zone out for a minute or two. This is the mathematical trick why that is possible. So um, in this case, let's do it for this example of LE and LF being 2. So we have two sums here. Um, so what that does, we have to sum over these things. Section. And we have basically then this product here that we sum over. This is actually correct. And we'll basically just literally spell that out. So this is usually an exponential explosion here. It's to the power of 2, so it's not that bad. But we go over all the possible values. So this is the row here where first a of 1 equals 0. So the English word is explained by the foreign word. So this is here, this is here, this is here. This is the first row. The second row, the English word is explained by the foreign word, word 1, and then the row after that is where the English word is explained by the foreign word number 2. That's the kind of outer loop. And then you see the inner loop where we start out with A2 being assigned to 0. So the second English word is explained by the 0th foreign word, so that is here. And then you can see that kind of going through there as well. Okay. I guess these colors make it a bit more clearer what's going on there. So when we see this, maybe one thing we can immediately think of, well, what this row here has in common is that it has the this part here, and we can actually pull that out. So if you pull that out, we are left with, let me actually do this with the colors, we're left with this here. This here, got the wrong green, but you get the idea. And then the last one here. So basically this, we pulled out that orange term here from that sum. So this is that line is then equivalent. Okay, and basically that's how it looks like throughout. We can do this for every line. So the second line, what does it have in common? Well, it has this term in common. And the third line, what does it have in common? It has this term here in common. And the thing that the sum that that term multiplies with is equivalent in each case. So the sum here is always the same. Okay, so that looks all the same. So we can actually do now the same thing. We can pull out that part. So I'm not going to go over all the colors here, but this part here, we can just pull it out as well and put it here. And then we're left with, on the right-hand side, all the different choices for here. So we have, again, oops, we have this here, with this here, the first term E given F0, we have a second here, E given F1, and then the third one here, where you have E given F2. So what we turned this into here is now a product of two sums. And that's basically what we want. So we now have a product over sums. So if you look at the previous slide, this is what all this enables here. So instead of having these endless sums, we now have a product over sums. Okay, you can start paying attention again. So this is basically from the pieces that we can now put together. Again, remember what we want to do really is we want to explain the probability of the alignment given the English and foreign sentence, and we're going to say, well, that's the probability of the English sentence and the alignment given the foreign sentence, that's IBM Model 1, divided by this P of E given F under any alignment, so that's why you have the sum over all the alignments. We have now both of these formulas. Up here is IBM Model 1 in all its glory, and at the bottom is the formula we just derived, which has this product over sums. This here cancels itself out. So I said right from the beginning, we don't need to worry about it too much. And actually, when we look at this closer here, we can even pull all this together even better and making this product over explaining each word divided by the sum over all the possible choices for it. So if you look at this a little bit more clearly, so basically what the choice is that we have to explain each English word and by what the alignment, what a particular alignment allows for it, divided by these English words being explained by any of the foreign words. So down here is what is this English word explained by all the possible foreign words, what are the choices, and then for each particular alignment, what's the probability for that. Okay, so this is a handy formula to get the probability of the alignment given the English and foreign sentence properly normalized. Okay, do we really care about this? No, we don't really care about this. We care about count collections. So this is what we do here. So here we actually go over the count collections. We have to collect the counts. So what we have in practice is someone gave us a nice English foreign sentence pair, and we want to get from that statistics for any of the English words in there and any of the foreign words in there, some counts that we're going to use for estimation. So we need the counts. Once we have the counts, then the estimation of the probability distribution is pretty straightforward. So what I'm saying here is what's the count collection for this English word and that foreign word given the sentence pair. So we have a sentence pair. We now want to collect counts for this English word given the line being aligned to the foreign word. So we sum over all the possible alignments. And so it's a probability of an alignment. And for each of the alignments, we here check, this is a Kronecker delta saying, is the English word E that I'm currently looping over the same as the EJ in that sentence? And here we're going to check, is the word F that I'm currently trying to collect counts over the one that EJ is aligned to, given under this alignment. So we have to sum over all the alignments here again. So we're going to do the same simplification as we just did, which turns this here into this formula here. So on the top here is the prior model's probability of E being explained by F divided by all the other probabilities of E being explained by the other F's in that sentence. So there's a bunch of F's in the sentence. Each possibly explains E. We sum over all that. And then that's the normalizing thing. The stuff here at the end is awfully complicated stuff to just ultimately what it does, it counts by how often E and F are aligned in the sentence pair. Why could that happen more than once is because maybe the word E occurs multiple times or the word F occurs multiple times. So this is usually one if E and F both occur in the sentence, but if E occurs multiple times or F occurs multiple times, it's basically the product of the number of occurrences of E and F respectively in the sentence. Okay, so we collect all these counts and that allows us then to estimate the model. So this is just basically, we're gonna sum over all sentence pairs. So we're gonna make a big loop over the entire corpus. Each one gives us some statistics. So this is just adding all that up. Probably while we go over the sentence, we actually carry out that sum. So we just accumulate values. And this at the bottom there is then the normalization. So these are counts that F maps into E, and then we have to go by F mapping into other E's. So normalized by that. Okay, here's some pseudocode for how this works. I'm not going to go into the narrating over this. It's mainly meant for you to look at and work your way through the algorithm. Let me just point out that this is the convergence over the entire loop. So we start with a uniform model and then we do the EM algorithm until convergence, and there are two steps. First of all, we initialize kind of count values, and as I said, I'm not going to go over the algorithm. You can kind of work your way through that in the slides. Okay, I do give you for this little toy corpus of now just two-word phrases. So das Haus being translated as the house, das Buch being translated as the book, and ein Buch translated as a book, and what happens there. So initially, so we basically have three English words, three German words. We're also going to introduce a null token. Oh, actually, no, we don't. We have four English words, four German words, and four English words. The four English words are house and book, an A, and four English words, and four German words, ein and das, Buch and Haus. So the initial probability distribution that we assign is 0.25. Each English word is equally likely aligned, explained by each individual foreign word. So when we run through the IM algorithm, this is how it looks like after the first iteration. So that's not entirely surprisingly. The word the, since it's aligned twice with das and only once with other words, it now has a preference for that, opposed to the other translations, and you can see what happens there. If you run this, this is what you end up with. So the final, if you actually would run this until emergence, you actually get perfect alignments out. Okay, here just a formal note. When we run this, we want to track progress. And the way we track progress is basically saying how well does the model fit the data. We don't know the truth. So we can't really measure by how well the model does against the truth. There's no truth given. Nobody ever gave us the proper alignment or the proper model. So all we can say is how well does the model fit the data. So that's something we can track. So we're going to compute perplexity by basically just saying how sure it is about sentence alignment probabilities. Okay, we went through all the core stuff. I'll quickly go over here what the other IBM models are, and then I'm gonna come back to the one mystery that I set aside at the very beginning, which had to do with one to many, many to many alignments. Okay, so we talked about IBM Model 1, lexical translations. The same principle is then being applied of estimating these models to slightly more sophisticated models. So IBM Model 2 adds absolute reordering model. So you basically have a probability that a word at position 1 maps to a word at position 1, no matter what that word is. Um, so that already gives you some kind of probably a model that should learn that word at position 1 most likely it aligns to word at position 1 and not so much as word position 2 or 3 or 4. But it kind of breaks down once you're at word 15. Should it be aligned to word position 15 or 13 or 14? Well, it depends a lot on the surrounding, what happened before and after. IBM Model 3 adds a fertility model. It basically says how many words a word might translate to. So it then learns things like uh, most words have one word translation, but we already came across the word klitzeklein that has two word translations. And IBM Model 4 fixes this reordering model to make it a relative reordering model. It just always looks at the previous word. What is the previous word aligned to? I should be somewhere in that vicinity. That makes a bit more sense and works better. And IBM Model 5 is just a technical fix that avoids that the previous models actually give probability mass to impossible alignment. So only IBM Model 1 actually has a global maximum. And computationally, the biggest challenge is in IBM Model 3. Once you add that fertility model, that trick we had that allowed us to do still kind of a proper solution to the problem of summing over all possible alignments doesn't work anymore. So we have to do other things, which is sampling, and then things get a bit more hairy. Okay, let me just talk a little bit more about word alignment as a problem and then the one technical fix to our IBM models. So word alignment is basically this problem here. You have an English sentence and a German sentence, and you want to find out the possible word correspondences. It's mostly a well-defined problem. So if you look here at Michael and Michael, well, that's the alignment and nobody's going to argue with that. You have things like assumes, which in German is more complicated phrased as geht davon aus. But then you also run into problems like what do you do with this comma? Yeah, that's not aligned to anything. It doesn't exist, but it's somewhat also related to that you have a subclause, and in German, when you have subclauses, you have to have a comma in English. You don't, so that maybe there should be alignment point here. Here's a more clearer example for the kind of arguments you have to go over. So in English, you have this negative construction does not live, so the word does occur in there, while in German it's just pretty much this means lives and this means not. So we're very clear about this point here, wohnt and live, and very clear about this point here, not and that. But what happens with the word does? You could say this is just some artificial token that doesn't have any correspondence to English. It just pops up in English for no good reason. However, it, for instance, carries the morphologically inflection of the verb, that this is a third person singular, which is in English, in German encoded in the morphology of the word, of the main verb actually. On the other hand, so you could say that should be an alignment point. On the other hand, you could make the argument this does occur only when a not occurs. So does not is pretty much a phrase that is equivalent to the not. So maybe that should be the alignment point. So you get into all these arguments, and it's not actually that clear and easy to align sentence pairs by hand. Here's another example. What if you have phrases that really, on a word by word basis, don't make so much sense? So here, John kicked the bucket, being an idiomatic phrase meaning that John died. An equivalent German expression would be John biss ins Gras, he bit into the grass. Okay, doesn't make more sense either. So what are you gonna do with that? You can really just say the phrase biss ins Gras and kick the bucket are equivalent. Well, on a kind of linguistic way, you could say kicked and biss are both verbs, and the is kind of contained in the ins here, and bucket and grass are both nouns, but kicked and biss are never really good translations outside this particular idiom, and bucket and grass um, are also not good translations outside this idiom. So how do you mark that up, and what do you want to get out of here? There's a way to measure alignment quality. This is the standard method for that. So the alignment error rate, it just basically checks how many word alignments that the algorithm produced maps to a human annotated word alignment, except the human annotated word alignment here also had possible alignment points. It basically dodges some of these decisions here and says, well, these are absolutely sure alignment points. So for instance, it would mark up here the the little square in in the gray area is these are definitely sure alignment points, and the other ones are optional. You may or may not get them. Okay, so we have IBM Model 1, which seems to be a solution to the problem, and we have the problem of word alignment. And why is that not enough? Well, the problem with IBM models is that we set aside at the very beginning was that they create a many-to-one mapping. So words are mapped with the alignment function. So a function may return the same value for different inputs. So we had that with very small, both very and small being aligned to klitzeklein. So we had two English words mapped to the same German word. That's still fine because we had, alignment of this here pointing to that and alignment of this here pointing to that as well. That was still fine. But we can't have multiple output values. We defined it as a function over input of integer to integer, so we can't suddenly return multiple values. A function can't have multiple values unless it's, returns sets. So we can't do that. But in the real world, and we actually showed an example, we have many-to-many mappings, or we have one-to-many and many-to-one and all that kind of stuff. So what's the solution? And this gets a bit hacky. So we run IBM model training in both directions. So that gives us two sets of word alignment points, and then we can take the intersection of these alignments. That gives us a high precision word alignment, or we can take the union that gives us a high recall word alignment. So the first time we get a lot of alignment points. We get few alignment points that are probably mostly correct. And here we get more alignment points. So we're probably going to get all the alignment points we should get, but they're less correct. So refinement methods explore the set of intersection and union. So let's just kind of go through that example. So here's an example of an English sentence. Mary did not slap the green witch. And here is the Spanish sentence. So the English to Spanish alignment. So you have here now English words aligned to multiple Spanish words. And here you have Spanish to English alignment, where you have Spanish words aligned to multiple English words. If you take the intersection, you end up with fewer alignment points, but they're probably all correct. And then in gray are the alignment points from the union, and we're going to add some of those. And the algorithm is really just a very simplistic heuristic that adds neighboring points. You actually see in research papers, even written today, this phrase here, grow diag final and. Means we're growing alignment points by adding neighboring ones, also diagonally neighboring ones. And then there is also a final step that says, well, if there are any unaligned words left, we should align them as well. And that and has to do with we only add unaligned words. So what do you do with this here? Should we align this with something? It's not explained by anything. The and says only if that alignment point connects words that are unaligned both in both languages. So in this case, this word, this alignment point after you already added this here is only unaligned in Spanish, but it's not. The English word is not unaligned. So with this and, we wouldn't add it. Without the and, you would add it. So that's it for today. So this was an introduction of IBM Model 1, so a very first and simple translation model, but I hope you got some insights about how you can learn word translations even if you don't have data marked up with alignments between words in a source sentence and words in a target sentence. Okay, that's it for today, and we'll continue next lecture by looking at a more sophisticated translation model called the phrase-based.